Hi, welcome back to Network Forensic Fundamentals. My name is Phil Hagen, and in this section, we're going to be talking to you about the Berkeley Packet Filter, what we call the BPF. Now, the Berkeley Packet Filter is a capability that is also provided by the libpcap library, which we talked about in the last video. And this is the filtering language. And the filtering language is important for us as forensicators because a lot of times we're going to look at a subset of the information that might be contained in an extremely large PCAP file, or maybe thousands of PCAP files. So these filters are things we need to use in order to reduce our scope. And we can do this through a lot of different filtering syntaxes. The BPF is one of those that's primarily built around the PCAP file format. Now, one of the cool things about the BPF is it is incredibly efficient. There's a whole lot of really technical, very low-level compiler-grade information behind that. I'll give you kind of the high-level overview, though. The Berkeley Packet Filter is so efficient because what you and I might type in on the command line or maybe in the user interface of a tool in order to filter our network traffic is actually compiled down into bytecode and executed in the kernel. That's what gives it its incredible efficiency and great speed. It's important to have that speed because that filter is applied to every single packet. Every single packet is going to be evaluated, and then a decision is going to be made on will this individual packet be handed off to the calling utility, or is it going to be ignored? Now, this is made on a packet-by-packet basis. You can imagine that that needs to be done extremely quickly. Think thousands or tens of thousands, maybe more packets per second being processed. The BPF ends up being a great way to do that. Now, the BPF is based on a concept of primitives, and this is just the fancy word for the different ways that you can filter the traffic. Now, it's important to know that these primitives are limited to values and fields that can be observed at layer 2, 3, or 4. And that's going to be the Ethernet or the other framing layer, the IP layer typically, and a layer like TCP or UDP. So those layers 2, 3, and 4 parameters are also what we're going to see in our available primitives. Now, some of these are very broad. I can say, just tell me what, just parse or handle what the packets that contain a certain protocol. I can say IP as a primitive, and that's going to limit it to just IPv4. If I want IPv6, I say IP6. I might go all the way up to layer 4 at this point. I might say, oh, I'm looking for only TCP traffic or UDP traffic. I can just specify those names, and it will limit the handling that's the calling utility does to just traffic that is one of those protocols. Between layers 2 and 4, though, we also have addresses. At layer 2, we have Ethernet addresses. Layer 3, we have IP addresses. Layer 4, we have usually ports. These can also be filter components within these BPF primitives. You can see here if I want to filter on something like the MAC address, I would use etherhost. If I want to filter based on an IP address, I would say host. That's only going to work for one individual IP. If I want to look for a net block or a network/net mask notation, it's called CIDR block notation, we would use the net primitive. If we're looking at ports, of course, those are port. Now, what's kind of cool about all of these address primitives is we can also be directional. I can prefix them with a source or dest, so SRC or DST indicator. So I can say source host or destination net. That ends up becoming really helpful when you're just looking at the single direction worth of traffic. And if you omit that, you just specify host or you just specify net, that's going to mean either direction. So it's not going to be specific. These BPFs can get to be quite complex. You can combine numerous primitives together using and or. You can negate them using not, of course, and or go in between two primitives. Not is going to prefix a primitive, so think not host and then an IP address. And we can also put parentheses in there, and these parentheses are going to enforce the order of operations. That order of operations is going to let you have very fine-grained control over exactly how the logic of your BPF is going to be executed. And if you're not familiar with this, it's very similar. It's identical to the handling that's done in basic arithmetic. Back in mathematics, the innermost parentheses are executed first, and then it goes out from there. Same thing happens here in the BPF. So it's very comfortable, very familiar to you with any kind of formulas that you might be used to. There's also quite a lot of other primitives, though. These are less common, but still demonstrate how powerful the BPF can actually be. If you're dealing with traffic that has VLANs, you can specify just a given VLAN or another. If you're only looking for, let's say, your guest network, and that's on a separate VLAN, you can limit that based on the use of that primitive. If I'm looking for a wide variety of ports that are contiguous, I can say port range. Maybe I'm just looking for traffic that is port 137, 138, or 139. I can say port range 137 to 139, and that will be those two endpoints and then everything in between. We can also get all the way down to evaluating individual byte-based math. And the example that you see here, IP and then the brackets, this is the indication that we're looking for a specific range of bytes. Now, the way this ends up working as it's written here is this BPF is looking for the single byte at offset 9 from the beginning of the IP header. So you can see the notation in the syntax that's used here. It's going to take that 1 byte and it's going to compare it to the hex value that you see on the other side of the equation. The hex value is 06. In reality, this is unnecessary. We actually already talked about a BPF that accomplishes the same thing. That was the word TCP, that initial primitive that we talked about up at the very top here. This is because the single byte at offset 9 from the beginning of the IP header indicates what the layer 4 protocol is. So what is the IP protocol? And if you look that up in any reference documentation like the RFCs, you'll see that IP protocol 6 is in fact TCP. And this actually brings us to a really important part about the BPF. I actually think it's one of the coolest parts of the BPF. Remember I said it gets compiled down into bytecode? It means that that compilation process is self-optimizing. It is incredibly efficient, not just because it executes in the kernel, but also because of that optimization that's done during the process of creating the bytecode. Now, what does that really mean to you and I as forensicators? It means that we don't have to get too creative and too tricky about writing our BPFs. We can write them intuitively because the optimizer is going to do its job very well, and it's going to make that as efficient as possible. If you look at these two examples over here on the right-hand side, these are exactly the same end result. And I've got the BPF written down below each of the flowcharts. And as you look at those two, you might say one or the other represents something that's a little bit more intuitive, a little bit more that it clicks a little bit better with you. Neither one is right, neither one is wrong. They're both equivalent. And you don't have to think about exactly what the logical evaluation is of each of those primitives and the order that they're executed in, because the optimizer is going to do you a solid favor and it's going to optimize it for you. Now, these are very simple examples. In looking at the flowcharts here, you might think one or the other of those is more intuitive, but again, it's all what that BPF is. Because think about this from the perspective of looking back at your case notes from 3, 6, 12 months ago. That BPF might be excessively long. You might have a 15, 20 component BPF. And if you do, it's going to be a lot better use of your time to read something that's intuitive that you can make sense of quickly, rather than try and figure out what convoluted logic you are trying to accomplish with a much more complex BPF. And the examples that you see here on the slide with the IP offset, 1 byte at offset 9, for most of us, that's going to take a little bit of research to go and figure out exactly what that byte is. Whereas if I say TCP, I just save myself some time. So don't worry too much about writing optimized BPFs. I guess you should say write human optimized BPFs, ones that you can understand, ones that you can easily explain to your colleagues as needed, because that compiler within libpcap is going to do a lot of the heavy lifting for you. That's just a brief look at the BPF. It's something that we use extensively when we're writing filters, because so many of our tools do use libpcap as a part of their builds, their compilation processes. And that means we get to use the BPF to process those PCAP files. So it ends up being a really efficient, effective way for us to take advantage of those. As we're going to look in some of our next videos, we're going to talk about some of our core tools that you're going to get to use in a real-world environment if you'd like to do so. And we're going to leverage these concepts of BPFs as well as PCAP files. So it's a great place for you to move into some of the tooling that we're going to be discussing as well. Hope you join us for more. My name is Phil Hagen, and this is Network Forensic Fundamentals.